Every year, over 50,000 tons of uranium are mined worldwide. But to get just a few grams of energy from it, you have to move mountains. It all starts in the desert, where the temperature reaches 100 degrees and ends in a reactor that powers New York. Here, centrifuges that spin faster than an airplane turbine, and substances that corrode metal in seconds. But the most interesting part is what even safety instructions don't talk about. Watch until the end, and you'll discover a secret that will change your perception of nuclear energy. It all begins in the dust. And that's not figuratively speaking. Uranium ore is mined in hot regions: Arizona, Wyoming, Texas, New Mexico. Sort of like cowboy landscapes, only instead of lassos, there are drilling rigs, and instead of a sheriff, engineers in anti-radiation suits. The sun here is scorching, up to 100 degrees Fahrenheit in the shade, if you can find any. There are two ways of mining: open pit, where the top layer of soil is removed and the ore is pulled out by excavators, and underground mining, with explosives, lifts, and ventilation that howls like an old tractor. And there's also the in-situ leaching method. Pipes are driven into the ground, and special solutions are pumped in to wash out the uranium directly from the rock, and then it's pumped back out. All this ore, a grayish-brown rock, looks no different from ordinary stones. But in it, uranium-235 is only 0.7%. The rest is almost useless mass that doesn't work in a reactor. And to squeeze the needed drop of energy from it, you have to process hundreds of tons. That's why they say nuclear energy is quite a marathon. After mining, the ore is crushed, ground, and thrown into a chemical bath. Acid or alkaline solutions are added to extract the uranium, like coffee from a filter. Then, filtration, precipitation, drying at 500 degrees Fahrenheit. And at the output, Yellowcake, a yellow, powdery concentrate. The official name is natural uranium concentrate, but everyone at the plants just calls it Yellowcake. It looks beautiful, mustard-colored, fluffy, like a spicy powder for barbecue. But God forbid you inhale or touch it. Alpha radiation, a long half-life, dangerous dust that penetrates the lungs and settles there forever. People work with it only in respirators, suits, behind 3 layers of glass protection. Yellowcake is packed into double-walled barrels, loaded onto trailers with an escort, and wrapped with radiation signs. And off it goes to the enrichment plant. It's from this poisonous dust that the journey begins, leading to the white light of a lamp over a kitchen table, or the electricity in the subway rushing under New York. Well then, Yellowcake is here, in barrels, radioactive and dry as a desert wind. The next step, turning it into a gas. And not just any lavender-scented gas, but uranium hexafluoride, the very same from which the required isotope for reactors and more is later separated. Let's cook, baby! The uranium concentrate is first dissolved in acid, purified, filtered from impurities, and converted into uranium dioxide. And here the magic begins. Uranium dioxide is treated with fluorine in special reactors at a temperature of 1000 degrees Fahrenheit. And as a result of the reaction, a volatile, transparent gas is formed, which boils at 133 degrees Fahrenheit. That is, you just need to heat it a little, and it turns from crystals into vapor. But it's not that simple. It is extremely toxic. It corrodes metals, destroys skin, and in humid air, it immediately turns into hydrogen fluoride and uranic acid. That is, a deadly cocktail. That's why all this is done in sealed, automated reactors that look more like devices from a villain's laboratory. Temperature, pressure, ventilation, everything is under control. Workers sit behind thick windows, monitoring the sensors. Any mistake, boom, or hiss, and you're already in a hazmat suit, scratching your heels on the way to the shower. This substance forms as solid whitish crystals when cooled to room temperature. These crystals are stored in steel containers, barrels with engravings, a batch number, and a radioactive sign. Each one weighs under 14 tons. And so, mission accomplished. The dust is turned into gas, ready for the most interesting part: isotope enrichment. But don't rush to celebrate. This gas is like a wild cobra. Beautiful, shiny, but if it bites, no one can save you. You think spinning a washing machine is fast? You haven't seen nuclear centrifuges that do 70,000 revolutions per minute. That's 10 times faster than an airplane turbine. And all for one thing, to separate uranium isotopes. The fluorine enriched uranium dioxide, that same poisonous gas we just made, is pumped into a tall, narrow cylindrical chamber, which is spun up to an insane speed. Centrifugal force does its thing. The heavier U-238 atoms fly to the edge, while the lighter U-235 atoms stay closer to the center. A tiny, microscopic difference, 1% in mass, and all this explosive technology spins just for it. But one centrifuge is not enough, so they are connected in cascades of hundreds, sometimes thousands. Each one slightly enriches the gas, then passes it to the next. And so cycle after cycle, until the U-235 content becomes at least 3 or 5%. This is the reactor standard. For weapons, of course, completely different routes are taken. They are classified and under strict international control. Okay, the gas is enriched, but in its gaseous state, it won't feed a reactor. So now it's converted again, this time into a solid ceramic form. After a series of chemical reactions with hydrogen, oxygen, and ammonia, the gas becomes uranium dioxide, a solid substance with a dark gray color. This powder is pressed under a pressure of 20 tons into small cylindrical pellets with a diameter of 3/10 of an inch. They look almost cute. But each such pill is like a charge of energy equivalent to 17,000 cubic feet of natural gas. Next, the pellets are sintered in furnaces at almost 3,000 degrees Fahrenheit to make them strong, like porcelain. Then they are polished, ground. Perfect dimensions are important for a tight fit in the cladding. The pellets are placed in long metal tubes, fuel rods, usually made of a zirconium alloy, because it doesn't rust, doesn't react with water, and withstands insane radiation. Over 300 pellets are placed in each rod. The rods are hermetically welded and combined into modules, fuel assemblies. They look like a frame of several dozen tubes, assembled in a square. One such assembly can weigh over 1,500 pounds and works for up to 6 years in a reactor. After assembly, testing for leaks, uniformity of filling, weld integrity, behavior under temperature. There are no trifles, because each of them can cost not just money, but lives. The finished fuel is packed in armored containers that can withstand impacts, fire, and falls from a height. Transportation is under guard on a special route with an escort, GPS, and mandatory. 2 seals, 3 codes, and a dosimeter on each side. Because even in its peaceful form, this is a dangerous thing that commands respect. After all this, what remains is depleted uranium hexafluoride. They call it tails. It's a mixture of isotopes where there's still a bit of uranium-235, but not much. These tails are stored in steel drums on special sites under supervision. But in the future, they can be reprocessed in new generation reactors, where everything will be squeezed out to the last drop. When a fuel assembly has served its 4 or 6 years in the heart of a reactor, it's no longer the shiny star it was at launch. It is removed, carefully, with a robotic system, and moved to pools of water. The depth is over 20 feet. The water cools and shields the radiation because the fuel is still hot, physically and radioactively. There it rests for several years. Then, 2 paths, either long-term dry storage in concrete containers with double walls, or reprocessing. In other countries, because the US mostly stores rather than reprocesses. In dry storage, the cassettes stand for decades, cooled by natural ventilation, as if in a nuclear monastery. This is not the end, but a new stage of life. Slow, controlled, but deeply connected to the future of energy. Because even after the reactor, this fuel remains a source of heat, a lesson, and a reason for respect. Did you know that over 100 million AK-47 pattern rifles have been produced worldwide since its invention? That's an absolutely staggering number, more than all the service rifles produced by almost every other country combined. This iconic weapon, recognized globally for its ruggedness and reliability, might seem incredibly simple on the outside. But producing these millions of units requires a massive, complex industrial process involving extreme forces, surprising precision, and manufacturing secrets perfected over decades. Get ready to go behind the curtain and see exactly how an AK-47 is manufactured on a colossal industrial scale. The story of the AK-47's manufacture really begins with its design philosophy. Mikhail Kalashnikov intended it to be simple, easy to use, reliable in the worst conditions, and crucially, easy and cheap to manufacture in vast numbers. This design genius meant engineers had to figure out how to make complex parts ruggedly and quickly. The key was often using methods that didn't require extreme precision machining on every single component, focusing tight tolerances only where absolutely necessary for function. This is a core secret behind its mass production success. One of the most visually impressive and important manufacturing processes for the AK-47 is IAE's stamping. Unlike many other rifles that use heavier, milled receivers, the AK-47 often uses a receiver made from sheet metal. Picture huge rolls of steel sheet being fed into massive, powerful presses. These presses stamp out the receiver's shape in stages, bending, forming, and punching the metal with tons of force. This high-speed stamping process is incredibly efficient, churning out receivers faster and cheaper than almost any other method. It's a core reason millions could be made. While the receiver is often stamped, many critical components that face extreme stress and heat, like the barrel, the bolt carrier, and the bolt itself, are made by forging. This involves heating steel billets, solid blocks of high-strength steel, to incredible temperatures until they're red-hot and malleable. Then, giant forging presses or hammers pound or squeeze these glowing pieces into complex shapes. The force involved is immense, thousands of tons, reshaping the metal's internal grain structure to make the part incredibly strong and durable. This is where raw power meets shaping, creating components tough enough to withstand the explosive forces of firing. Even though simplicity was key, certain areas of the AK-47 require remarkable machining corrode, precision for reliable function. The bolt, which locks into the receiver, and the chamber end of the barrel, where the cartridge sits, must meet tight tolerances. These parts are finished on computer numerical control machines that use hardened cutting tools to shape the tough steel with incredible accuracy. While not every surface needs mirror-like precision, the critical interfaces that ensure safe and reliable firing are machined to exact specifications, often measured in thousandths of an inch. Bringing all these parts together involves other vital metalworking processes. Welding is used to join stamped receiver components and attach parts like the gas block to the barrel. Industrial welding robots, or skilled human welders, create strong, reliable joints. Heat treatment is also critical. Components like the bolt and bolt carrier undergo processes like hardening and tempering, heating and cooling cycles that change the steel's properties, making them incredibly resistant to wear and impact, vital for the rifle's legendary durability in harsh conditions. Once all the metal components are fabricated and treated, they often go through finishing. This includes processes like parkerizing, bluing, or applying polymer coatings. These aren't just for looks. They're crucial for protecting the metal from corrosion, especially important for a rifle designed to operate in wet, muddy, or humid environments. Furniture, the stock, handguard, and pistol grip, is often made on separate lines from wood or polymer, and then added to the metal assembly. The final stage is corrode assembly. While many steps are automated, putting together the hundreds of components of an AK-47 often still involves significant human skill on assembly lines. Workers fit parts together, install springs, pins, and levers, turning a pile of components into a functional rifle. Each rifle is inspected visually and functionally as it comes off the line. The true test of an AK-47's manufacturing is its legendary reliability, and this is verified through rigorous quality control and testing. Rifles are subjected to dimensional checks and material tests. Crucially, they undergo proof testing, firing rounds with an intentionally heavier charge than standard to ensure the weapon can safely withstand extreme pressure. Some are even subjected to brutal environmental tests, dunked in mud, buried in sand, submerged in water, and then expected to fire immediately. This extreme testing validates the ruggedness built into the manufacturing process. Producing millions of AK-47s requires vast factory complexes, intricate logistics, and a highly skilled workforce. It's a fascinating intersection of design philosophy, focused on simplicity, and industrial processes capable of achieving rugged reliability on an unprecedented scale. While the rifle itself is often seen as a symbol of conflict, its manufacturing process is undeniably a powerful example of mass production engineering and durability-focused fabrication. So, the next time you see an image of that instantly recognizable silhouette, remember the unseen journey it took. From raw steel and wood, through giant stamping presses, powerful forging hammers, precise machining centers, intense heat treatments, and rigorous testing, it's a product of a massive, impressive industrial process. It's a fascinating look into the power and precision that builds one of the world's most widespread tools. What part of manufacturing an AK-47 surprised you the most? Let us know in the comments. Now, can you just picture this? Every single day on this planet, folks burn through over 9,900,000 barrels of oil. That's like what? 1 billion liters. Pretty wild to think about, right? But what is oil, really? How does this thick black goo actually get turned into the energy that powers our entire world? Today, we're gonna dive deep into the seriously fascinating world of oil production. We'll start with how it even forms over millions of years, then check out the incredible tech in modern wells that punch down tens of thousands of feet into the earth. We'll cover everything from those giant platforms way out in the middle of the ocean to the complex refining steps that take that raw material and turn it into clean fuel. Ready to find out the real story behind that black gold? Let's just jump in and see how natural gas really works. Folks are projecting that average oil production in the United States next year is going to hit right around 9,900,000 barrels per day. But honestly, do you even know what oil is? Or where it even came from in the first place? I mean, everybody talks about oil this, oil that, oil spills, oil production. But nobody ever really tells you what it actually is. Well, stick with us, and we'll just break it down for you. The way oil forms is a seriously long-term project, taking millions of years. It kicks off with a bunch of organic stuff, like the leftovers from ancient plants and little critters, piling up on the bottom of old seas and lakes. Over time, these plant and animal remains get buried under layers of sedimentary rocks, things like clay and sand. Then, under a ton of pressure and heat, which gets way more intense the deeper you go, that organic material starts transforming into something called kerogen. It's kind of a solid, waxy material. If the temperature keeps cranking up, hitting somewhere between 140 and 302 degrees Fahrenheit, that kerogen breaks down using heat. And bam! You end up with liquid hydrocarbons. So, yeah, that's us your oil. If you didn't find that interesting, seriously, let us know what you think is cool. Just write it down. Okay, so the oil that formed just like we explained, it actually travels through porous rock until it runs into something called a trap. Think of that as a geological structure that just stops it from moving any further. It starts building up there, and bingo, you've got yourself an oil field. It's kind of fascinating that scientists are still having debates about the exact details of this whole process, and whether oil might form in other ways too, not just from ancient organic bits. People started pulling oil out of the ground way back in ancient times. But the real deal oil boom didn't kick off until the 19th century. That's when the kerosene lamp came along. To actually get your hands on the oil, the absolute first step is figuring out precisely where it's hiding. This phase, geological exploration, is easily one of the toughest and most expensive parts of the entire oil extraction game. Scientists aren't just walking around with shovels, you know? They're using satellite images, magnetometers, seismic waves, and other super high-tech methods. Seismic surveying is actually pretty spectacular to witness. They set off controlled underground explosions in a specific area, or use special vibrating platforms to create waves that travel down through the rock layers. These waves bounce off different layers in the ground and come back up, and sensors pick them up. It's like building a three-dimensional picture of what's underground, essentially letting them see beneath the surface. Once the geologists pinpoint a promising spot, the actual drilling kicks off. A rig, whether it's sitting on land or floating out in the ocean, turns into this giant humming machine that runs non-stop 24/7. The drill string, those are steel pipes with a cutting bit on the end, bores into the earth, spinning at up to 200 rotations per minute. To keep the drill bit cool, carry rock pieces out, and stop the hole from collapsing, they pump in drilling mud. That's a thick mixture, usually water or oil-based. Modern wells can go seriously deep, ranging from 10,000 feet down to 16,000 feet. And sometimes, way deeper, up to 35,000 or even 40,000 feet. For instance, over in places like Texas or Saudi Arabia, they're drilling wells that stretch over 26,000 feet long. And often, a big section of the well goes sideways, horizontally. This lets them tap into a much bigger chunk of the oil reservoir without having to drill a bunch more vertical wells. One of these operations can cost you anywhere from a few $1,000,000 to easily tens of millions of dollars. And honestly, it doesn't always work out successfully. But if the well does turn out to be a producer, oil starts making its way to the surface, either pushed by its own natural pressure or pulled up with pumps. And that's when the next big stage begins, actually getting the oil out, processing it, and shipping it off. Speaking of major producers, Saudi Arabia is right up there as one of the biggest oil producers globally. Just back in February, Saudi Arabia was pumping out nearly 9 million barrels of oil every single day. This country actually has a solid chance to boost its standing in the energy market even further, especially since Saudi Aramco recently announced they found 14 brand new oil and gas fields right there in the country. So, once all the exploration and well drilling is completely finished, the absolutely crucial stage begins, actually pulling that oil out of the ground. If the field is really rich, the oil itself might just start pushing its way up to the surface simply from its own pressure. That's what's traditionally called a gusher. And while it might look pretty dramatic, with those big streams of black liquid shooting up into the air, these days, that method is seen as pretty old school and kind of dangerous. Modern wells are outfitted with sophisticated systems of valves and regulators that allow them to precisely control the pressure and the volume of oil that's flowing out. The oil gets to the surface through a network of pipes, and then it heads over to what's known as a processing facility. That's where they separate it from other stuff that came up with it, like associated gas, water, sand, and whatever else is mixed in. This step often happens right there at the extraction site, either on those big platforms out in the ocean or at bases on land. Separating all those impurities is a pretty cool process to watch. The oil mixed with all the extra stuff goes into this large, sealed tank, and gravity gets to work inside. Gas is light, so it floats up to the top. They collect it through an upper outlet. Water is heavy, so it settles down to the bottom. They drain it off through a lower valve. Oil is in the middle in terms of density, so it hangs out between those two layers. Now, if tiny droplets of water get kind of stuck in the oil, it's not quite as simple to separate them out. That's when they might add something called demulsifiers. These are chemicals that break up that mixture. Or they might heat the oil up a bit, which also helps those different layers split apart. But hey, let's get back to the extraction itself. Sometimes, to increase the pressure down in the rock formation, they use what are called secondary recovery methods. For instance, they might pump water, gas, or even steam into other wells. This helps to kind of push the oil towards the well they're actually producing from. Technologies like this can help them pull out up to 60% of the oil reserves from a field, whereas without them, that number could be cut in half. The average amount of oil a modern well in the United States produces is anywhere from 500 to 1,500 barrels per day. Just think about that for a second. 1 barrel is 42 gallons. Now multiply that by the thousands of wells operating all over the planet. And that really gives you a sense of the true scale of oil extraction. Oil by itself is actually a really complex blend of hundreds of different hydrocarbons, ranging from those lighter gases all the way up to heavy fuel oils. To get gasoline out of it, that's that light, easily ignitable part that internal combustion engines can use effectively. The raw material goes through several technically tricky stages at an oil refinery. It all kicks off with something called fractional distillation. Crude oil is first heated up to temperatures between 660 and 750 degrees Fahrenheit and then fed into a distillation column. This is a tall tower where the temperature gets cooler as you go up. Different components of the oil vaporize and rise to different heights, where they cool down, turn back into liquid, and are collected at various points. The gasoline part, it's one of the lighter ones, is typically collected at levels corresponding to temperatures between 104 and 392 degrees Fahrenheit. But simply distilling the crude oil isn't quite enough to get high-quality gasoline. You only get about 15 or 20% of the gasoline fraction this way, and most of what comes out still has stuff you don't want in it, and an octane number that's just too low. To boost the total amount of gasoline they get, they use a process called cracking. This is basically all about breaking down those long hydrocarbon molecules into shorter ones. The most common way is catalytic cracking, where heavier parts are heated up to almost 1,000 degrees Fahrenheit in the presence of catalysts. This lets them get extra gasoline from those heavier leftovers. Sometimes they also use hydrocracking, which involves hydrogen under high pressure. When it's all said and done, the percentage of gasoline you can get from just 1 ton of oil can reach 40 or 50%. That depends, of course, on the type of oil and how sophisticated the refinery is. The gasoline they get from these cracking steps usually has a low octane number, meaning it would cause knocking or detonate too early in an engine. To fix this, they put it through a process called reforming. This means rearranging the structure of the molecules at high temperatures, usually with platinum catalysts present. This really boosts the octane number, potentially all the way up to 98, making the fuel perfectly suitable for today's cars. In the very last step, they mix additives into the gasoline to improve how it works. This includes things for anti-corrosion, preventing engine knocking, cleaning the engine, and reducing environmental impact. This helps keep the engine healthy, cuts down on harmful stuff coming out of the tailpipe, and makes the fuel more efficient overall. Just one modern oil refinery can process up to 400,000 barrels of oil every single day. That's pretty impressive, especially when you stop and think that daily gasoline consumption in the United States is roughly 370 million gallons. Besides going to our homes, natural gas also gets sent to power plants, factories, and chemical facilities. For big industrial users, they need way higher pressure and volume. They're using pipes with diameters up to 48 inches and pressures up to 1,500 psi. Gas can even be turned into a liquid. They cool it way, way down and ship it in massive tankers across the oceans. Are you ready to peek into a world where millimeters decide life and gleaming metal travels a path from a piece of raw material to deadly precision? Imagine this. Over 12 billion rounds of ammunition are produced worldwide each year for the military, police, hunters, and athletes. And each one is the result of precision engineering, where temperature, pressure, and shape matter down to the last decimal place. In this video, we'll show you everything. From selecting gunpowder and alloys for the casing, to control tests where the muzzle velocity is almost 300,000 feet per second. Get ready. This isn't just a story about bullets. It's a journey into the heart of modern manufacturing, where technology and science operate at the edge of what's possible. Hundreds of millions of bullets roll off factory assembly lines around the world every year, and each one passes through quality control lines with micron-level precision. The primary material is brass, an alloy of 70% copper and 30% zinc. It's ordered in massive rolls about 0.06 inches thick and weighing up to 6,000 pounds. These rolls are supplied by metallurgical plants, most often in the United States. These are companies like Olin Brass or Chase Brass. The rolls arrive in sealed packaging to prevent oxidation during transport. Upon arrival at the factory, the brass is uncoiled on a special platform and fed into a rolling machine, a huge heated steel drum. The metal's temperature at this stage reaches 600 degrees Fahrenheit to make it more pliable. The brass is flattened. Any deviation means rejection. Next, the brass sheet is fed into a press line, a high-speed stamping press that, with lightning precision, punches out small discs, so-called blanks. Their diameter is approximately 0.75 inches, and their thickness matches the original sheet. The press operates at up to 250 strokes per minute, so every second yields a new batch of blanks. The resulting discs are heated to 800 degrees Fahrenheit. This is necessary for the subsequent deep drawing process. They are dipped in lubricant and fed into a hydraulic press, where, under pressure of up to 100 tons, the disc is formed into a primary casing, still without details, just a cylindrical shape. This process is repeated several times, each time drawing the casing a bit longer and thinner. At this stage, the blank already resembles a casing, but is still far from its final appearance. Each casing is annealed after drawing. This involves heating it to 1,000 degrees Fahrenheit to relieve internal stress in the metal. Otherwise, the casing could crack during firing. Then, it's cooled in water and cleaned in an acid solution to remove scale and lubricant. Next, calibration and weighing. The casings pass through a high-precision laser control system. A weight discrepancy means automatic rejection. Length, wall thickness, cylindricity, and even acoustic response are similarly checked. Special sensors detect if a casing has microcracks or internal defects. Finally, the casing is trimmed to the exact length, a groove for the primer is cut, and the mouth is expanded to accept the bullet in the future. Then it either goes to the final assembly line or is packaged for separate sale. Casings are bought for sport shooting and military orders alike. The next critical stage is primer installation. This is a small but extremely important component that initiates the explosion. The primer is a miniature explosive device. Inside a metal cup is a primary detonator, usually based on lead styphnate or lead-free substitutes. Before installation, primers are checked for sensitivity. Those that react to a weaker impact or have an unstable explosive concentration are rejected. On an automated line, each casing passes through a priming station where, with incredible precision, a mechanism inserts the primer into the rear of the casing and crimps it so it doesn't fall out during recoil. Next, gunpowder. The type depends on the ammunition's purpose. For pistol rounds, most often spherical smokeless powder. For rifle rounds, extruded powder in the form of small tubes. On average, one .223 Remington round contains about 24 grains of powder. For comparison, a 45 ACP round contains only 5 or 7 grains. Gunpowder is measured automatically to the thousandth of a grain. Too much or too little is a danger to the shooter and the weapon. An error of 1/10 of a grain is unacceptable. Some systems use real-time optical scales that react even to vibrations in the workshop. Once the powder is loaded, it's time to seat the bullet. The bullet itself is another story. Material, shape, mass. Everything depends on the task. Hunting, military, sports, defense. But seating occurs with the same precision. The bullet is pressed under pressure into the casing, and then the mouth is crimped so it doesn't pop out during feeding into the barrel. After this, final calibration and visual inspection by eye through a camera with a neural network that manages to analyze each round in less than a second. The rejection rate is less than 0.3% at large enterprises. And only after all stages of inspection, calibration, and final weighing does the bullet reach the final phase: packaging. Packaging isn't just about aesthetics or ease of transport. It's a matter of protection, identification, and logistics. Because when you're shipping 50,000 rounds to a single client, mistakes are not forgiven. It all starts with counting. Bullets are automatically sorted into trays or fed onto weighing lines, where batches are formed in quantities of 20, 50, 100, or 1,000 pieces, depending on the customer's specifications. The cheapest packaging option is plastic trays with shrink wrap. This is a budget solution for the civilian market, convenient for shelves and mass sales. Military supplies are packaged differently, in zinc or steel containers with airtight lids. Inside, liners with anti-corrosion treatment, markings with caliber, lot number, manufacturing date, and QR codes. One such box holds from 1,200 to 1,500 bullets, with a total weight of up to 40 pounds. In some cases, containers with moisture control systems, or even built-in trackers for delivery monitoring. On industrial lines, one shift packages from 100,000 to 300,000 bullets. Some factories operate in 3 shifts, 24/7, especially during periods of high demand such as military contracts, crises, or elections in the United States. The productivity of one packaging machine is up to 12,000 units per hour. In workshops with gunpowder, primers, and explosives, there is anti-static flooring. This is a special coating that diverts electrostatic charge from a person's body or equipment to the ground to prevent sparks that could cause explosions or ignition of explosive substances. Also, the humidity in the workshop is maintained at 40 to 60%, which reduces the risk of dust or particle ignition. In areas with metal dust, oil vapors, and fumes from galvanizing, ventilation with filtration is mandatory. Workers wear special suits made of natural fabrics or anti-static materials. It is forbidden to wear metal objects, watches, jewelry, or phones. Only certified specialists are allowed in the gunpowder or primer areas. Access is strictly biometric. People do not touch gunpowder by hand. Everything is handled through sealed automated systems. Primer formation, explosive mixture dosing, casing sealing, all are maximally automated. Robots or shielded machines handle the most dangerous stages. Powder fire extinguishers, sprinkler systems, and special containers for isolating ignition are placed every 150 feet. Personnel undergo mandatory training every 3 or 6 months. Evacuation, firefighting, first aid. All casings, bullets, and primers undergo visual, weight, and X-ray inspection. Rejects are sent to separate safe zones where they are disposed of or recycled. The factory is guarded like a high-security facility. Video surveillance, armed guards, inventory of every unit. In 1998, in the United States, a plant manufacturing gunpowder for sport ammunition exploded due to violations of storage rules. Several types of mixtures with different properties were stored nearby. The explosion's power was equivalent to several tons of TNT. 4 workers died. The investigation revealed dozens of systemic violations. Therefore, safety at such plants is more important than the product they manufacture. Imagine this: red-hot metal, up to 33 feet long, being pushed with a dull roar into a massive rolling mill. No seams, no joints, just a perfectly smooth steel pipe appearing literally out of nowhere. These aren't scenes from a science fiction movie, but the daily work at one of the most unique factories in the world. How is it possible to create a pipe without a single seam? One that withstands pressure of hundreds of atmospheres and operates where other materials simply melt. Ready to walk through the scorching workshop and find out how true engineering perfection is born? Then let's embark on a journey to an amazing steel pipe factory. It all starts with cylindrical billets. Each one weighs 1 ton. That's like 3 smart cars in a metallic body. They are transported by rail or truck because other transports simply can't handle such a load. Each billet is secured on special pallets or in retaining clamps so it doesn't shift during movement. Upon arrival at the factory grounds, unloading is automated using cranes, manipulators, or hydraulic carts. The billets immediately go to the receiving area, where they are checked for compliance with technical specifications: chemical composition, shape, integrity. Before the hot steel becomes a pipe, it undergoes a truly dramatic inspection. Defects shall not pass. First, the billets get an X-ray. Well, not exactly X-ray, but something similar for metal: ultrasonic testing. You heard that right. The billet is coated with a conductive gel, like for a human ultrasound, and a transducer is moved across it. Special transducer ears shoot sound waves at a frequency of 5 megahertz. That's 100 times higher than submarine sonar. This is how they search for cracks and inclusions of foreign materials within the billets. The system builds a 3D map of defects with an accuracy of 1/100th of an inch. If it finds a saboteur, the billet is marked with red paint and sent to metal hell for remelting. Next comes the chemical analysis. For this, 5 or 10 metal samples are taken from each batch and sent to the factory laboratory. There, they use special spectrometers, devices that read the metal's composition using light emissions. The spectrometer determines over 12 elements in the composition in seconds. During the analysis, the sample is treated with an electric spark or a laser. This excites the atoms on the metal surface, causing them to emit light of different wavelengths. Each chemical element glows uniquely, so the device recognizes exactly which elements are present in the steel and in what quantities. How much carbon, manganese, chromium, nickel, or phosphorus. This analysis takes only a few minutes, but provides a complete picture of how well the billet meets technical requirements. If the composition isn't perfect, the batch might be rejected or redirected to other production lines. From 1 to 3% of billets are sent for remelting. Defective billets are sent to an electric furnace with a temperature of 2,900 degrees Fahrenheit, where the steel becomes liquid again. All the post-melting slag is used for road construction. 90% of defects are detected during the ultrasonic diagnostic stage. It's like finding a needle in a haystack in 10 seconds. The chemical analysis takes 17 seconds, faster than you order coffee at Starbucks. Quality control costs range from $50 to $100 per ton of steel, but it's better to overpay than to later have a well blowout due to low quality material. Quality control is the Karen's filter for steel. Only 97 to 99% of billets become pipes. The rest are sent for reincarnation. So, when you hold coffee in a steel thermos, know this: its ancestors went through real metal special forces training. After checking the chemical composition, the cylindrical steel billets are delivered to the heating section, the place where a giant furnace stands. These furnaces are true giants, capable of holding over 1,000 billets simultaneously. To load the billets inside, massive automated cranes or special manipulators with heat shields are used. The billet is picked up using gripping mechanisms, large metal fingers or tongs that securely hold the heavy part. The crane carefully moves the billet to the open loading door of the furnace. At this time, the temperature inside can exceed 2,400 degrees Fahrenheit, so the entire process is maximally mechanized. People operate the machinery remotely from a safe cabin or control panel. The furnace has special guides or pushers that help place the billets carefully inside, so that heat distributes evenly. After loading, the furnace doors are hermetically sealed, and gradual heating to the working temperature begins. In 2 hours, the steel transforms into a plastic mass. The billet becomes ready for forming, like melted chocolate. Next, the monster drill comes into play. It weighs 12 tons. That's like 2 elephants. The red-hot steel billets, massive cylinders, are removed from the furnace and delivered to a special rolling machine, where one of the most crucial stages of seamless pipe production begins, creating the hole inside. The piercing process looks impressive. The red-hot billet is placed on a special support ring in front of the piercing mill, where a thick, cone-shaped rod awaits it, the so-called piercer point or piercing mandrel. At this moment, immense force is at work. The billet is rotated between 2 conical rolls, spinning in opposite directions. The rolls don't just squeeze the billet, they create strong rotational and axial pressure, causing the billet to stretch along its axis, flowing around the piercer point. To avoid cracks or ruptures, the pressure and temperature during piercing are controlled very carefully. If the billet cools too quickly, or the pressure is distributed unevenly, it can break or lose the required shape. Therefore, the process runs without interruption and with strict adherence to all parameters. This process is called the Mannesmann method, named after the German engineers who invented it in 1885. After the initial piercing, the resulting rough pipe is called a hollow shell or bloom. The wall thickness of the shell is approximately 2 inches. It still has uneven walls and may contain small defects, so the next stage is rolling and calibration, where the pipe is stretched, straightened, and brought to the required dimensions and wall thickness. The red-hot steel billet enters under giant rolls 5 feet in diameter. Under tremendous pressure, it's drawn out into a slender pipe up to 40 feet long, faster than you can blink. This is where the major league of precision reigns. Wall thickness is reduced from 0.8 inches to 1.2 inches, with a deviation of less than 0.004 of an inch. That's thinner than a human hair. And all this happens at staggering speeds of 16 to 49 feet per second, faster than Usain Bolt on his best day. It's like rolling out the thinnest pizza dough. Only instead of dough, it's a red-hot steel core. And instead of a kitchen board, there's a shower of sparks and the roar of the rolls. Next, fire gives way to ice. Well, not ice, but cooling. The workshop heat is 122 degrees Fahrenheit, so workers wear special suits as if preparing to conquer Mars. Meanwhile, the pipes gradually cool in the open air. Their temperature slowly drops to 570 degrees Fahrenheit to avoid deformation and cracking. When the pipe emerges from the fiery dance of rolling, it resembles an enraged dragon, powerful, but bent into wild spirals. That's when the 8-roll giant enters the scene, a mechanical Hephaestus that will forge perfect forms. Its rolls, stronger than the rocks of Olympus, bend the steel with a force of 500 tons. That's like putting 250 Land Rovers on the pipe. But this force isn't a destroyer, but a surgeon. It corrects curvatures smaller than the thickness of a hair. And then comes the time for lasers. They scan every millimeter, finding the smallest defects, invisible cracks, minor unevenness. And when they find something, plasma scalpels enter the game. 10 times hotter than lava, they cut the metal like cosmic lightning bolts. All that remains of the defects is smoke and legend. If the Colossus of Rhodes were made of such pipes, it would still be standing today. Every year, the world produces over 10,000 tons of titanium discs, the material used to create the hearts of airplanes, implants for surgeries, and even parts for spacecraft. A single disc can weigh more than a smart car, but it fears neither temperatures of 1,800 degrees Fahrenheit nor the vacuum of space. How does a gleaming superdisk, capable of withstanding thousands of revolutions per minute, emerge from a gray, spongy mass. What do aviation, medicine, and the titanium hell of furnaces have in common? This isn't just manufacturing. It's a show of strength, precision, and engineering magic. Let's dive into a world where metal takes on its perfect form. Titanium discs are blanks shaped like thick discs made from titanium or its alloys. They serve as the starting material for parts in highly critical fields: aviation, medicine, space, energy, and automotive manufacturing. Titanium is a true superhero among metals. It's lightweight yet extremely strong, withstands insane temperatures, resists corrosion, and doesn't react with the human body. That's why it's used for everything, from aircraft components to implants. But pure titanium is a bit finicky. It's difficult to machine and can be brittle under certain conditions. Therefore, it's often mixed with other elements, creating alloys. The most popular alloy consists of titanium with 6% aluminum and 4% vanadium. It's strong, wear-resistant, and easier to form. Aluminum adds lightness and heat resistance, while vanadium adds flexibility. For medical devices, pure titanium or alloys without toxic elements are used. Depending on the task, titanium can be harder, more ductile, or more resistant to extreme conditions. That's why manufacturers choose not just titanium, but the specific alloy that perfectly meets the particular challenge. Titanium for discs comes from titanium sponge, the primary raw material extracted from ores, mainly ilmenite and rutile. The largest deposits of these ores are found in Australia, South Africa, China, Kazakhstan, and Canada. But the sponge itself is produced where complex manufacturing facilities exist because the process of converting ore into metal is very energy intensive. It all begins with a dirty grey, pumice-like substance, titanium sponge. It arrives at the plant in large containers and bears almost no resemblance to the future aerodynamic part. But this is where the journey starts, ending with the gleam of a perfectly polished disc capable of withstanding thousands of revolutions per minute. First, it's checked for impurities and moisture. Acids or solutions that react with impurities are used, removing them from the titanium surface. This process might involve treating the raw material in special baths. Titanium parts might also undergo abrasive treatment, such as grinding or sandblasting, to remove surface contaminants. After cleaning, the titanium raw material undergoes heat treatment to improve its structure. The raw material is heated to a specific temperature, usually between 1,300 and 1,600 degrees Fahrenheit, and held there for a defined period. This helps reduce internal stresses that might have occurred during previous processing stages. If necessary, the raw material can be heated to higher temperatures to achieve homogeneity in the alloy structure. This ensures an even distribution of elements within the material, enhancing its strength. After heat treatment, the titanium undergoes a fascinating rapid cooling stage, which is quite a spectacle. When the metal is removed from the furnace, it glows with bright shades of red and orange, reflecting the high temperature it was heated to. Cooling can be done in several ways, by quenching in water or by air cooling. When submerged in water, you can observe the hot titanium creating foam and bubbles as it rapidly contacts the liquid, emitting a characteristic crackling sound. This is visually impressive, as the boiling water witnesses an incredible transformation, from a potentially malleable state to a strong metal. Alternatively, air cooling is calmer, but no less captivating. The metal gradually loses heat, changing its color and texture. This process, although less dramatic, demonstrates the smoothness and elegance of titanium's transition to its final form. Then, the material is loaded into special crushers or hammer mills. The main purpose of crushing is to reduce the particle size of the titanium, facilitating further processing and ensuring material uniformity. The crushed particles can be used in various processes, such as producing powder alloys or forming new parts. After crushing, the resulting particles may be washed to remove residual debris or impurities. They are then dried in preparation for further processing. To manufacture the titanium discs themselves, the blanks are heated to high temperatures, typically up to 1,500, or even 1,800 degrees Fahrenheit. This is done to make the titanium softer and easier to work with. The heated blank is placed in a press or hammer. Impact action or pressure shapes the blank into the desired disc form. During this process, the titanium undergoes significant deformation, leading to changes in its structure. For casting, however, special molds are made, usually from steel or cast iron. The molds must be very precise to ensure the correct geometry of the disc. The titanium is heated until it turns into a liquid. This is usually done in vacuum furnaces to prevent oxidation. The liquid titanium is poured into the prepared mold. After cooling, it solidifies, taking the shape of the disc. Casting allows for the production of discs with complex shapes that are difficult to achieve by forging. Now it's time for machining. Before machining, the discs are cleaned of dirt and residues. For this, they are immersed in a special bath with a solution that removes slag and grime. The water foams up, and the disc becomes clean. Next, the discs are secured on lathes for stability during machining. A lathe is used to remove material from the edges of the disc, achieving the required diameter. Thin metal shavings curl away from the cutting tool like a slender snake. The contours and profiles of the disc are formed according to technical specifications. If grooves or holes are needed, a milling machine is used. Then, the discs are processed by grinding machines to achieve the smoothest possible surface. This is important for reducing friction. Finally, they are polished to obtain a shiny surface, which also enhances their aesthetic qualities. Polishing can further protect the disc from corrosion. After polishing, the surface becomes smooth, reducing the likelihood of dirt and moisture accumulation. Fewer imperfections and cracks mean fewer chances for corrosion. Polishing also seals microscopic pores that can retain moisture and contaminants. This significantly reduces the risk of oxidation. Afterward, the disc is inspected for scratches, cracks, or other visible defects. Calipers and micrometers are used for precise measurements of the disc's diameter and thickness. To detect internal defects not visible on the surface, ultrasonic testing is performed. This inspection method does not require direct contact with the disc. A special transducer emits ultrasonic waves into the disc material. As the waves travel through the disc, they reflect off boundaries such as defects or the material itself. The time it takes for the waves to return to the transducer is measured. This allows for the detection and sizing of defects. Specialized software analyzes the received data, providing information about the disc's condition. This is a very fast process, allowing many discs to be checked quickly. Titanium is 40 times lighter than steel, but has comparable strength, making it ideal for the aviation and automotive industries. It does not rust or corrode in most environments, making it a durable choice for various applications. In the United States, an average of 10,000 to 15,000 tons of titanium is produced annually. A significant portion of this amount is used for manufacturing discs and other components. Thus, on a monthly basis, this could amount to 800 to 1,200 tons of titanium discs. Leading companies in the United States, such as Boeing and Lockheed Martin, actively invest in the production of titanium discs to meet the needs of their programs. It is expected that in the coming years, the demand for titanium discs for aviation will grow by 5 to 7% annually, especially considering new technologies and increased aircraft production. Every year, over 2 billion cacti are grown around the world. And we are not just talking about your grandma's windowsill plant. They are crushed into cosmetics, tossed into salads, turned into textiles, and even transformed into cactus leather. The largest plantations stretch across thousands of acres in Mexico, Italy, and the United States. These plants grow without a single drop of irrigation, absorb carbon dioxide better than trees, and thrive in places where even weeds seem exhausted. Cacti are charging into the future, and not just in flower pots. In this video, we will show you how they are grown, why the world needs so many cacti, and how they might just help save the planet. In the United States, cacti have long outgrown the souvenir market. They are cultivated for cosmetics, pharmaceuticals, bioleather, livestock feed, and even as an edible superfood. While most people associate cacti with Mexico, it is actually the United States that has become one of the leaders in industrial cactus farming. The United States was not always at the top in this field. Mexico traditionally held that title, where cacti are a national plant, a food source, and a cultural symbol. But starting in the 2000s, when the global boom for superfoods, vegan products, and eco-friendly materials began, American farmers and startups saw a golden opportunity in cactus farming. They figured, quite reasonably, that the climates of Texas, Arizona, and California are ideal for growing prickly pear, nopal, and other species. Plus, the United States has a huge market of consumers seeking healthy, vegan, locally produced goods. So, the demand was already there. Many agricultural startups received grants, investments, or government support to launch sustainable cactus farms. Fast logistics, existing processing infrastructure, and support for small agribusinesses all played a major role. By the 2010s, especially after 2015, farms started popping up not just for food, but for cosmetics, medicine, and leather. And since 2020, when the world embraced alternative materials and zero waste, the United States has stormed into the top producers of cactus-based bioleather. Now, American plantations supply products both domestically and for export to Europe and Asia. The largest plantations are found in Arizona, Texas, California, and New Mexico, regions with dry climates, lots of sun, and very little rain. In Maricopa County, for example, cacti are cultivated across dozens of acres of open land. The main variety here is prickly pear, prized for its fast growth, edible fruits, and industrial applications. It all starts by selecting the hardiest, most productive cacti, those that have shown strong resistance and consistent yields. For instance, a single prickly pear plant can produce 20 to 30 fruits in one season. Farmers cut a segment from the parent plant, usually one pad or shoot, and dry it for 3 to 10 days so the cut seals and does not rot in the soil. These cuttings are then planted in a sandy clay substrate, sometimes directly in open fields, sometimes in containers for rooting. The rows are spaced 3 to 5 feet apart to allow equipment access and minimize light competition. Cacti take 3 to 4 weeks to root, and the first fruits or shoots appear after 6 to 12 months, depending on the variety and climate. During that time, farmers monitor humidity and temperature. Once the first plants are well established, the farm expands by taking new cuttings from these fresh plants. This creates a stable, nearly self-sustaining system. So, it all begins with one spiky stalk, and within a year, it can produce dozens of new ones. To keep a cactus field looking like a postcard-worthy Mexican paradise, it needs real maintenance. Sure, cacti are desert survivors, but once you grow them by the ton, they become a little more delicate than the ones on your windowsill. On a commercial scale, drip irrigation is used, a system of tubes that slowly but steadily waters each plant. The average is 4 to 8 gallons per plant per week, depending on the climate. Next comes pest protection. The biggest threat is not rain, but cochineal. This fuzzy white bug looks like a cute puffball, but drains the sap out of plants faster than you chug a smoothie on a hot day. Then there are spider mites, nematodes, and other microscopic monsters. What do farmers do? They use biocontrol. They release predatory insects to hunt down the pests. It is like Game of Thrones, in bug form. Sometimes they also use natural insecticides, like garlic-based sprays or neem oil. Cacti prefer nutrient-poor soils, but a little boost never hurts. Once a season, farmers add compost or a special blend of nitrogen, potassium, and phosphorus. It is all done by the book, between 11 and 22 pounds of fertilizer per acre. Otherwise, you will end up with a jungle, not a farm. Harvesting on large cactus plantations is not some old guy with a machete. It is a full-blown operation. Harvest usually happens in the morning, before the sun turns the fields into a frying pan. Workers wear protective gear, because those spines are no joke. They trim ripe fruits or pads with special knives, or even mechanized tools. one person can harvest between 1,000 and 1,500 pounds of raw material a day. And if the farm is automated, that number can double. The most popular varieties, nopales and tuna, go on to be sorted. Each plant gets inspected: size, weight, color, and damage. Some fruits are automatically weighed, scanned, and sent down a conveyor. Premium ones head to supermarkets. The rest go to processing or canning. Workers manually inspect up to 1,000 units per hour, so the concentration level is like the final scene of a TV drama. The biggest farms use computer vision systems that sort out defects and count yields. Sorted cacti are packed into boxes or plastic crates, labeled and prepped for shipping. Shipping cacti is all about delicacy and timing. Packed in ventilated containers, they are loaded into refrigerated trucks. The temperature stays between 40 and 50 degrees Fahrenheit to prevent the cacti from turning into mush. On average, one truck carries about 40,000 pounds of product. If it is for export, cacti may travel thousands of miles to Europe, Canada, or Japan. To keep everything fresh, logistics must be timed down to the minute. And a little bit of luck helps. No one wants to open a box of shredded, spiky bits instead of bright green segments. Young prickly pear pads are no longer exotic. In major supermarkets in California, Texas, and Arizona, nopales sit right next to broccoli and romaine lettuce. And yes, they go on sale on Fridays. They are often sold pre-cleaned and sliced into strips, cubes, or thin rounds, or pickled in jars with peppers, garlic, and onions, basically like Mexican pickles. Nopal juice or powder is added to smoothies and supplements. It is good for digestion, helps manage blood sugar, and is considered a superfood. Fried with eggs, cactus is a classic breakfast dish. Think of it like Mexican scrambled eggs with a tangy green twist. It also goes in tacos and burritos, adding texture and a slightly slimy but pleasant acidity. Prickly pear tastes great in salads with tomatoes, feta cheese, peppers, and cilantro. It is also baked with cheese or meat as a side dish, or turned into cactus lasagna. The taste? Well, it is an acquired one. A bit like green bell pepper, a bit like beans, with a slight tang and a slippery texture. If you do not roast it well. But once you try it, you often come back. Do you like the taste of nopal? Share your favorite recipes. If you think cacti are just about spines and sand, you're missing the big picture. They store water in their stems for years. Like real soil-based banks, they hold reserves for hard times. In deserts, they become water distributors for entire ecosystems. Nopal, like many other cacti, is also used in folk medicine for treating everything from diabetes to digestive issues. Its gel helps heal wounds and prevents scarring. In some countries, cactus-based cosmetics are common. Nopal gel is often found in moisturizing creams and serums. Its texture allows it to penetrate the skin quickly without leaving a greasy residue. It is known that nopal extract has a calming effect, helping reduce inflammation from sunburns or skin irritation. The oil extracted from cactus seeds, especially prickly pear seeds, has become a star ingredient in cosmetics. Rich in fatty acids and vitamin E, it is a powerful antioxidant. Prickly pear seed oil helps reduce wrinkles and improve skin elasticity. It also soothes and nourishes the skin, preventing dryness. That is why it is often added to eye creams, where it helps reduce dark circles and puffiness. Cactus extracts are also used in hair products. The oil and nutrients help strengthen hair, add shine, and improve scalp health. They may reduce hair loss and stimulate growth while moisturizing dry scalps. Some cactus-based products even offer UV protection. Extracts can form a natural barrier against the sun's harmful rays, helping prevent sunburn and irritation. Brands like Kiehl's, Fresh, and Herbivore Botanicals already use cactus extracts in their products. Facial creams, serums, shampoos, and hair masks featuring cactus are especially popular. Nopales can live for decades. Some cactus species even live for centuries. For example, the saguaro, the giant cactus, can live up to 200 years and grow to 40 feet tall. That is about 1 inch of growth every year. And it is not just the stems that are edible, the flowers are too. Prickly pear flowers, which often bloom red or orange, can be tossed into salads, brewed as tea, or used as edible decorations on dishes.